Hey, morning, guys. Hope you guys are having a good spring break so far. Let's go ahead and do this lecture real quick. So, evolution, evidence, part one. This is where we're really going to start talking about the evidence revolution. I know we did a little bit with fossils in the activity we did last week, but here we're actually going to really get to the heart of some of the big pieces of evidence we have for why we know evolution is actually something that happens every day, and natural selection is what causes it, right? So, structural adaptations. That's the first one. It's really kind of straightforward. So it's basically populations of organisms will inherit traits that give them structures that help them survive. Simple enough, right? Obviously, if an organism has a trait that's going to help it survive over another organism, it's going to survive better, and it's going to pass on more offspring to the next generation, right? So that means that more of their genes are going to go to the next generation, and that means that more of the selected trait is going to be passed on. So a great example of this are peppered moths in England. They're a great example of structural adaptation. So what's really awesome about these guys is that these species of moth live in England, right? And they like living on trees a lot of the time outside. So that's why this one on the left here looks like that, because if you guys have ever seen like a birch tree, that's kind of what a birch tree looks like, right? It's like a white tree with these little like black specks on it. And that's what the moths looked like for thousands of years, to blend in on the birch tree so they wouldn't get eaten by predators. Then in the 1800s, the Industrial Revolution happened. And when the Industrial Revolution happened, they put up a ton of factories in England, and they started putting out a ton of soot from the factories, which made everything black. And what happened is all the white birch trees would be colored completely black. So before, there were some black moths, but they got eaten pretty quickly by predators because they stuck out really easily on the trees. But after the trees turned black, what do you think happened? Right. What happened was all of the black moths started doing really, really well when all the environment around them was black, because now they had camouflage, and these white moths started dying. And so what's actually really, really cool, even more cool than the initial adaptation, is after they started getting rid of all the factories, after the Industrial Revolution, after they started cutting down on pollution, and the trees went back to normal, we've actually seen as the black moth population has gone down a lot, and the normal white and black speckled moths have come back. So that's just a really cool example of how evolution is working in real time. Fossil evidence. So this is one we talked a lot about, so I'm going to go over it a little bit more quickly than the last one. So paleontologists figure out how the organism was adapted to the environment, how we can use that looking at the fossil record of what we know about the environment at the time that the organism was alive. We can also look at what traits the organism had and say, okay, this thing has webbed toes, it obviously probably lived in the water, right? And so we can group organisms using the fossil record. What I mean by that is we can actually use the fossil record to put them in order of when they were alive. More than 99.9% of all species that have ever lived on Earth have become extinct. That is crazy. Like, think of all the organisms we have alive today. That's only 0.1% of all the life that's ever existed on Earth. The Earth is much, much older than we usually give it credit for. In order to be classified as a fossil, it must be at least 10,000 years old. That's a pretty arbitrary number. They just kind of picked it because it's a nice even number, but that's what we use. So if it's at least 10,000 years old, it is officially a fossil. And the fossil record is incomplete because not all organisms that die become fossils. It's actually really darn hard to become a fossil. So basically what has to happen, as we can see in this nice little graphic over here, so in this case, this fish dies and sinks to the bottom of a lake. The soft parts of the fish rot and get eaten, like we talked about, right? And it leaves only the bones. So then the bones are going to be covered with mud. And after millions of years, mud is going to turn into rock, and the bone matter is completely changed into mineral or rock, right? And so the fish is now a fossil. And the reason I use this picture is it's a lot easier for fossils to be made in the water, because in the water, they can get covered up by sediment a lot more quickly than on land. And also a lot of times at the bottom of lakes and oceans and stuff, there's just less like bacteria to break them down than there would be like in dirt on the surface of the earth and air. But it can happen in air, it can happen on land, as obviously we see all these dinosaur fossils, but just what has to happen is they have to get covered up really quickly. So like there's a really famous fossil example of this velociraptor and this Protoceratops fighting, and they got covered with a sand dune, actually. Like, they lived in the desert and a sand dune covered them, and that actually fossilized them really quickly. So, transitional fossils. We talk a lot about, or we don't, but people say, you know, oh, where's the fossil in between this and this? Where's the evidence? We have them. We really do. So here's one example, is Archaeopteryx. So if you guys have looked at this since I've started talking, this looks like a bird, right? But this is actually a transitional fossil between a bird and a dinosaur. So that's what the fossil that we originally found, the Berlin specimen, looks like, and that's what a recreation of what it would have looked like when it was alive. So it looks like a bird, and that has the beginnings of a beak. It has feathers, obviously. That's a huge bird trait. But at the same time, it still has these little fingers like a dinosaur would. It has kind of feet that look more like a dinosaur, and it has teeth. So this is actually really, really cool, because it turns out that birds are kind of descendants of raptor-like dinosaurs, like Velociraptor that you see in Jurassic Park. And this was really the first piece of evidence we had for that. Another transitional fossil that's really cool is, we have this guy. This guy's name is Tiktaalik. And he lived 375 million years ago. And by the way, Archaeopteryx lived 150 million years ago. But Tiktaalik is the transitional fossil between fish and amphibians. So this guy was the first fish that started coming out onto land. That's what he looked like in fossil form. That's a recreation of what we think he would have looked like when he was alive. And what's really cool about him is you can actually see him start to develop kind of feet-like structures with his fins, right? They're not totally on the side for swimming anymore. They're actually able to support some of his weight and drag him along land, which is really awesome. All right, another example we have are homologous structures. So homologous structures are a great example of common ancestry. Basically, it's when these homologous structures have different adult forms, but they originate from the same embryonic tissue. What we mean by that is, so in a human embryo and a cat embryo, let's say, because they're right here, they have the same tissue for their forearms. Now, our arms and a cat's paw come from the same embryonic tissue. It's the same stuff, but it makes different forms. And you can see that here. So the different bones are different colors. So we have this bone right here, so there's a cat, and then the whale's is this little thing, this little stub, kind of up there at its shoulder. And the bat has one that's more like ours. And then if we look down here, we've got these guys, they do as well, going all the way across, and then even our fingers, right? So our fingers are obviously just these part of our hands. A cat's finger is actually the bones all the way in what we'd consider its paw, right? Because their wrist is actually all the way up there. Whales, most of the length of their arm is their fingers, and bats is kind of this, looks more similar to us. So that's actually really cool that all these different mammal bones have the same initial bone structure. It's just changed to look different, right? It's just changed in different forms that make them more adapted to whatever their environment is or whatever their function is. Analogous structures are kind of homologous structures in disguise. They're trying to be homologous structures, but they're not. So analogous structures are structural features that do not have a common ancestral origin, but they're similar in function. So this is saying that although they do the same thing, they're not evidence of a common ancestor. So here we see the bat and bird wings. Those are examples of a common ancestor because the bones in each of those arm-like structures end up creating these kind of these limbs that are used for flight, right? And it's the same kind of bones in each of the two organisms. However, if we look at an insect wing, so this is dragonfly wings, it's not the same at all. They don't have any bones in their wing. So that is an analogous structure because they have similar function, which is being made to fly. They don't have a similar ancestral origin. And vestigial structures are really, really cool. Vestigial structures are structures that have no function in the present-day organism, but they were probably useful to an ancestor. So really small legs in whales that we sometimes see, tails in humans, the appendix in humans, which actually there's some research coming out it might not be a vestigial structure at all because it might be a kind of sanctuary for gut bacteria that we need to survive, and wisdom teeth. So if you guys, I don't know if you guys know this, like 65% of all people get their wisdom teeth removed, which is crazy. That's because we don't really need them anymore, and they take up too much space in our mouth. The mini legs in whales is a great example. So baleen whales have these pelvic bones, right? They have these bones in their body, but they're not connected to the rest of their skeleton. They don't really do anything at all, but they still have them. That is great evidence of them having ancestors that used to have legs, because they still have these vestigial structures, they still have these pelvic bones, but they don't do anything now. So how did they get there if they don't do anything? What's the point? Well, maybe they're left over from when they had ancestors that had legs. And that's actually true. We found fossils, and whales' closest ancestor are actually pigs, which is pigs and hippos, which are really, really cool. Closer to hippos than pigs, but that's pretty awesome. And so it turns out that whales' ancestors kind of looked like hippos, and they had legs, but they kind of went into the ocean and went back to living that way. The last piece of evidence we're going to talk about is embryology, which is also super cool. So if you look at the embryonic development of vertebrates, so animals with backbones, they look remarkably similar to each other, especially the earlier in development you look. So all embryology is saying is that if we look at the embryos of different vertebrates, animals with backbones, we can actually see really similar structures. So this is the end product, at the very bottom here. This is where all the embryos become really, really specialized. You can see there's a human, there's looks like a sheep or something, and there's a bird and a turtle. They look all really different, right? Well, let's go all the way back up to step 1 up here. They look really, really similar. That's because all of these organisms start off with the same general structure, and then different genes are turned on or turned off, and that's what makes them into all these different organisms at the end. So I hope that was helpful for you guys. I'm probably going to post another lecture on Sunday night that's going to be over the stuff we're going to be talking about on Wednesday. You don't have to watch it until Tuesday night if you don't want, but feel free to. And I will see you all on Tuesday. Have a great rest of your break. I really hope you guys are enjoying it.